Good morning, students. Students, we should start our syllabus of 12th science in the subject physics. Today I am discussing the topic. Name of the topic as kinetic theory of gases and radiation. Friends, in the old syllabus, actually there were two topics separately. Firstly, kinetic theory of gases and secondly, radiation. Today I am discussing only the part of the radiation in new syllabus included of 12th science physics. Myself, Dr. V.S.Savant, lecturer in physics, Department of lecturer in physics, Shivraj College, Gadhinglaj. Introduction. We know that there are three modes of transfer of heat energy, namely first conduction, second convection, third one radiation. So we know that what is conduction. We define conduction, that is the mode of transfer of heat energy through the material medium without actual migration of the particle from body at higher temperature to body at lower temperature. That means the particles are not migrating, and we know that heat always flows from the body at higher temperature to body at lower temperature. Here particles are not vibrating, or we can define the conduction in other words, that is the mode of transfer of heat energy through vibratory motion of atoms and their collision with neighboring atoms or molecules. Here molecules or atoms, they are colliding with each other, and according to the phenomena of collision, when two bodies collide, they will transfer either momentum or energy. So here vibrations of the atoms causes the transfer of energy, and due to this transportation the atoms vibrate with large angle. Secondly, we define convection, that is mode of transfer of heat energy through the material medium with actual migration of the particle from body at higher temperature to body at lower temperature. That means in convection the particles are actually migrating. Then third one, that is radiation. We define the radiation, that is process of transfer of heat by radiation does not require any material medium, since electromagnetic waves travel through vacuum. Or in other words, we can define the radiation as the mode of transfer of heat energy by means of electromagnetic waves for which material medium is not necessary is called as radiation. Then following are the properties of the radiation. If we compare the mode of transfer of heat energy, that is conduction, convection and radiation. Conduction is slower mode of transfer of heat energy. Convection is faster mode of transfer of heat energy than the conduction, but slower mode of transfer of heat energy than radiation, and radiation is faster mode of transfer of heat energy as compared to conduction and convection. So radiation is faster mode of transfer of heat energy. Secondly, it does not require the material medium, because we have already stated in the definition that the radiation travels by means of electromagnetic waves, and electromagnetic waves are non-mechanical waves, and for which material medium is not required. So it does not require a material medium. Thirdly, radiation refers to continuous emission of energy from the surface of any body because of its thermal energy, and this emitted energy is called as radiant energy. And remember that the emitted energy is also in the form of electromagnetic waves. Then lastly, the electromagnetic radiation emitted by the bodies which are at higher temperature with respect to the surroundings is known as thermal radiation. Next, then the first point in the topic, that is interaction of thermal radiation and matter. So in examination's point of view, the question may be asked like this: define coefficient of absorption, define coefficient of reflection, define coefficient of transmission, and derive the relation between three coefficients, that is coefficient of absorption, coefficient of reflection, and coefficient of transmission. So here, suppose that capital Q be the total amount of thermal energy incident on the surface of an object, and we know that when heat radiations are incident on the object, then heat radiation may be absorbed, they may be partially reflected, or they may be partially transmitted. So depending upon the partial absorption, reflection and transmission, we denote the quantities. Let QA, QR and QT be the amounts of heat radiations absorbed, reflected and transmitted by the body. Then by using conservation principle of energy, the total incident heat or total amount of thermal energy is equal to sum of three components, that is Q equal to QA plus QR plus QT. Divide this equation by capital Q, we get Q upon Q, that is Q get cancelled, left hand side becomes 1, equal to towards the right hand side QA upon Q plus QR upon Q plus QT upon Q. Then we define coefficient of absorption or absorptive power or absorptivity. The coefficient of absorption is defined as the ratio of amount of heat absorbed to the total quantity of heat incident on it, and it is denoted by letter small a. Small a is ratio of QA to Q. QA is amount of heat absorbed and Q total amount of heat energy exit. So QA upon Q is nothing but coefficient of absorption. Secondly, we define coefficient of reflection or reflectance. It is defined as the ratio of amount of radiant energy reflected to the total energy incident. Then it is denoted by letter small r. Small r is ratio of QR to the Q. QR is amount of heat reflected by the body and Q is incident heat. Similarly, by changing the word, that is absorbed or reflected by transmitted, we ultimately define the coefficient of transmission or transmittance, that is the ratio of amount of heat transmitted, instead of absorbed you can say transmitted, to the total quantity of heat incident on it. It has notation TR, or sometimes say the notation small t, that is equal to ratio QT upon Q, where QT amount of heat transmitted and Q, that is amount of heat incident. Then putting this value, we get sum of the three components, that is equal to 1, that is A plus R plus T equal to 1. Then we know that coefficient of absorption, reflection and coefficient of transmissions, they are ratio of the similar quantity, and that is why they are unitless quantity, also they are dimensionless quantity. Then The physical significance of this equation, that is A plus R plus T equal to 1, it indicates that if coefficient of reflection is 0 and coefficient of transmittance is 0, then coefficient of absorption A equal to 1. That means all the incident energy is absorbed by the object, and such an object is called a perfectly black body. In other words, for perfectly black body, coefficient of absorption is 1, coefficient of reflectance and transmittance, they are 0. Secondly, if we substitute coefficient of transmission T or TR equal to 0, then also A equal to 0 substitute in this equation. So T and A are 0. We get only R equal to 1. That means all the incident energy is reflected by the object. That is, the object acts as a perfect reflector. Then we can say that a good reflector is poor absorber and poor transmitter. Then following are the factors, depending on which factors this coefficient of absorption, reflection and transmission depends. These three coefficients depends upon, firstly, the wavelength of incident radiation. Secondly, this coefficient depends on the material of the object on which it is incident. Then, depending upon whether the substance can transmit the heat radiation throughout it, or whether the substance can transmit heat radiation, we can classify the substances as diethermanous substances and ethermanous substances. Firstly, we discuss diethermanous substances. Definition: the substances through which heat radiations can pass is known as diethermanous substances. Examples of diathermanic substances are glass, quartz, sodium chloride, hydrogen, oxygen, dry air, etc. Secondly, ethermanous substances. We define the ethermanous substances as the substances which do not transmit the heat radiations are called as ethermanous substances. Or in other words, the substances which are opaque means they are not transmitting heat radiations. So the substances which are opaque to the heat radiations are called as ethermanous substances. Examples of ethermanic substances are water, wood, iron, copper, moisture, benzene, etc. Then next point in your syllabus, that is perfectly black body or ideal black body. Firstly, we define what is made by perfectly black body. Then secondly, we can discuss the properties of the black body. So definition of the perfectly black body: the body which absorbs all the heat radiation incident on it is called as black body, or it is called as perfectly black body. Then for perfectly black body, the coefficient of absorption A must be equal to 1. Of course, the coefficient of reflectance and transmittance, they are 0. And by Kirchhoff law of radiation, coefficient of absorption is equal to coefficient of emission. So if A equal to 1, ultimately for perfectly black body, coefficient of emission also become equal to 1. So these are the properties of the perfectly black body. Now question arises is that whether the perfectly black body exists in practice or not. So the answer is no. It is impossible to obtain a perfectly black body. However, for the practical purpose, The lamp black or platinum black, they are treated as perfectly black body, because the lamp black or platinum black, that can absorb nearly 97% of heat radiation incident, and they act as a perfectly black body. Now the scientist Ferri designed the perfectly black body. This is the diagram showing Ferri's black body. What is the construction? It consists of double-walled sphere having a small aperture or say small hole and conical projection opposite to that of the aperture. The inner wall of the sphere is coated with lamp black, or say inner wall of the sphere coated with perfectly black body. Then outer wall of the sphere is polished, that means silver polishing is on the outer wall of the sphere. Then the space between inner and outer wall is evaporated space. Now what is the working? The radiation will enter inside this sphere through this aperture. When radiations enter inside the sphere, there occurs multiple internal reflection inside the sphere. Within one reflection, 90% of heat is absorbed, and therefore all the radiant heat, it will be absorbed by the body, and hence the scientist Ferri's black body can be given credit as a perfectly black body. Then both the scientists, namely Lummer and Prinsep, performed the experiment on the black body. Both the scientists, Lummer and Prinsep, they heated the black body at a different temperature. They observed the color of the black body at a different temperature. Finally, they plot the graph. Graph is nothing but black body radiation spectra. What is the quantity on y-axis? That is the radiation intensity. That is intensity as a function of wavelength is taken on the y-axis. And on the x-axis, the wavelength is taken in micrometer. And these are the different temperature ranges. There were two observations. Firstly, suppose that these temperatures are kept constant. Then what happens? When temperature is constant, intensity of radiation increases with increase in wavelength, reaches to the maximum value at a particular wavelength, say lambda max, and with increase in the wavelength, intensity of radiation goes on decreases. So this is the first observation. When temperature is constant, intensity of radiation increases with increase in wavelength, reaches to the maximum value, and intensity of radiation goes on decreases with increase in wavelength. Secondly, when temperature is not constant, then the curve is not uniform. That means the peak of the graph of radiation intensity versus wavelength is not uniform. So it indicates that as the temperature increases, the peak of the graph, it is shifted towards the shorter wavelength side. Note that the scale, this is the origin of the graph, and there are smaller wavelength present at this scale, and this wavelength increases away from the x-axis. Then area under the curve represents the amount of radiation emitted by the black body per unit area per unit time. Or in other words, the area under the curve represents the emissive power of the black body. Then from the black body radiation we state the law called as Wien's displacement law. Why the law is called as Wien's displacement law? Because from the graph we know that as temperature changes, the peak of E lambda versus wavelength, it is shifted towards the smaller wavelength side, and that is why the law is called as Wien's displacement law. Then the law states that the wavelength for which emissive power of the black body is maximum is inversely proportional to the absolute temperature of the black body. Or we can say, in other words, the wavelength for which intensity of radiation is maximum is inversely proportional to the absolute temperature of the black body. Mathematically, we can write lambda max inversely proportional to temperature, where lambda max, it is the wavelength for which black body has maximum emissive power, or lambda max, it is the wavelength for which intensity of radiation is maximum, and capital T, absolute temperature of the black body. Then a lambda max is inversely proportional to temperature. Remove this proportionality sign, introduce the constant. This equation becomes lambda max into T equal to constant. That means the product of maximum wavelength and absolute temperature remains constant. The proportionality constant is called as Wien's constant, and it has value Wien's constant B equal to 2.897 into 10 raised to minus 3 meter Kelvin. Then we define emissive power or radiant power. So emissive power or radiant power is defined as the amount of radiant heat emitted by the body per unit area per unit time. So we know that amount of heat radiated by the body depends on, firstly, the absolute temperature of the body, that is capital T. Secondly, it depends upon nature of the body, whether it is perfectly black body or ordinary body. Then depends upon the nature of the material, also depends upon nature of the surface, whether the surface is polished or not. Then also it depends upon surface area of the body, and finally amount of heat radiated by the body depends upon time small t for which heat is passed, or small t the time duration for which the body emits the radiation. So we define the emissive power or radiant power once again, that is amount of radiant heat transmitted by the black body per unit area per unit time. So remember this formula, R equal to Q upon AT. What is Q? Q is amount of heat radiation, capital A surface area of the body, and small t, that is time. Then what is the physical significance of this equation? If we take Q upon A, we get amount of heat radiated by the body per unit surface area. If we take ratio Q upon T, then it gives the rate of emission, that is amount of heat emitted per unit time, and Q upon AT represent amount of heat radiated per unit surface area per unit time. Then SI unit of the emissive power, we know that heat is measured in the form of energy, or heat and energy are equivalent. SI unit of heat is calorie, equivalent to joule. SI unit of area, that is meter square. SI unit of time is second. So put this unit inside the formula. Unit of Q, that is joule, divided by meter square. It can be written as m raised to minus 2 divided by time, that is per second. So SI unit is joule per second per meter square, and we know that joule per second is SI unit of power, that is watt, and hence this unit gets simplified. It becomes watt per meter square. So say SI unit of emissive power, that is joule per meter square per second, or watt per meter square. Then the dimensions of the emissive power, that is L raised to 0, m raised to 1, and t raised to minus 3. Then we discuss the next article, that is Kirchhoff law of heat radiation and its theoretical proof. Firstly, statement of the Kirchhoff law of heat radiation. It states that at a given temperature, the ratio of emissive power to the coefficient of absorption of a body is equal to the emissive power of a perfectly black body at the same temperature for all wavelengths. That is, according to formula or according to statement, Rb is equal to R upon A. What is Rb? Rb is nothing but emissive power of the perfectly black body. Capital R, emissive power of the ordinary body, and small a, that is coefficient of absorption. So according to the statement, the ratio of emissive power of ordinary body to coefficient of absorption, that means right hand side of this equation, is equal to emissive power of the black body. Or in other words, we can state the Kirchhoff law of heat radiation as for a body emitting and absorbing thermal radiations in the thermal equilibrium, emissivity, that means coefficient of emission, is equal to its absorptivity. Absorptive means coefficient of absorption. So according to this statement, when a body is emitting or absorbing the thermal radiation, when the body is in thermal equilibrium, coefficient of absorption is equal to coefficient of emission. The physical significance of this equation is that if a body has higher emissive power, it also has higher absorptive power. Conversely, if a body has lower emissive power, it has also low absorptive power. So this is the statement of the Kirchhoff law of heat radiation. We have to prove that either Rb equal to ratio R upon A, or we have to prove that coefficient of absorption is equal to coefficient of emission. So next slide shows theoretically the Kirchhoff law of heat radiation. Let define the various notation. Let A be the ordinary body, capital B perfectly black body, capital R the coefficient of capital R emissive power of ordinary body A, Rb emissive power of perfectly black body B, capital Q amount of heat radiation incident on each body in unit time. Let Qa quantity of heat radiation absorbed by the ordinary body A. Then we can apply the equation for ordinary body A as quantity of heat radiation absorbed by ordinary body, that is equal to quantity of heat radiation emitted by the body. So quantity of heat radiation emitted by the body, that means rate of emission, and quantity of heat radiation, heat absorbed by the body, that is rate of absorption. So rate of absorption is equal to rate of emission. According to definition of emissive power, this becomes AQ, that is rate of absorption, that is equal to rate of emission, that is R. Write this formula for perfectly black body. For perfectly black body, we know that coefficient of absorption is 1. So 1 into Q, that is Q, equal to, as it is, replace R by RB, because RB is nothing but emissive power of perfectly black body. Now divide these two equations. In the left hand side, AQ upon Q, Q get cancelled, only A is remaining here, equal to, as it is. Then right hand side, ratio R upon RB. Then simplify this equation, transfer A to the right hand side, transfer RB to the left hand side, we get R upon A equal to RB. Also we know that R emissive power of ordinary body, RB emissive power of perfectly black body. So ratio of emissive power of ordinary body to the emissive power of the perfectly black body is nothing but coefficient of emission. Put this value in this equation, we get coefficient of absorption, that is equal to coefficient of emission. Thus we have proved the Kirchhoff law of radiation theoretically, that is coefficient of absorption, that is equal to coefficient of emission. In next slide, we can discuss the Stephens-Boltzmann law of radiation. So statement of the Stephens law of radiation, it states that the rate of emission of radiant energy per unit area or the power radiated per unit area of a perfectly black body is directly proportional to the fourth power of its absolute temperature. Or in other words, I can say that the emissive power or radiant power or radiant energy, emissive power of perfectly black body is directly proportional to the fourth power of the absolute temperature. Mathematically, RB proportional to T raised to 4. So RB, emissive power of the perfectly black body, T raised to 4, that is fourth power of the absolute temperature. Remove this proportionality sign, introduce the constant, that is sigma. We get RB equal to sigma T raised to 4, where sigma is proportionality constant known as Stephens constant, and it has value 5.67 into 10 raised to minus 8 joule per meter square per second per Kelvin raised to 4. Also we know that joule per second is SI unit of power, that is watt. So this unit becomes watt per meter square per Kelvin raised to 4. Then for ordinary body A, we can write emissive power of ordinary body capital R equal to E into sigma T raised to 4. Because sigma T raised to 4 is nothing but emissive power of the perfectly black body, and we know that R upon this sigma T raised to 4, that is RB, R upon RB is equal to E according to Kirchhoff law of radiation. So after modifying, we get for ordinary body emissive power of ordinary body R equal to E into sigma T raised to 4. Then put the value of R, that is Q by 80. I am writing this formula for perfectly black body, that is R, that is becomes Q upon 80 equal to, according to this statement, emissive power of the black body equal to sigma T raised to. Then applications of Stephens law of radiation for calculating the energy radiated per unit area per unit time, also heat absorbed per unit area per unit time, and loss of heat per unit area per unit time. Suppose that capital T absolute temperature of the black body and T0 absolute temperature of the surrounding, then by using the definition of emissive power of a perpetual black body and by using the Stefan's fourth power law, I can write the energy radiated per unit area per unit time, that is Q by AT is nothing but sigma T raised to 4. Then energy absorbed from the surroundings per unit area per unit time, only replace T by T0, so this becomes sigma T0 raised to 4, that is energy absorbed from the surrounding per unit area per unit time, because the black body can absorb the heat from the surrounding and temperature of the surrounding is T0, and according to Stefan's fourth power law, here is written sigma T0 raised to 4. Subtract these two equations and take sigma common, we get loss of energy by the perpendicular black body per unit area per unit time, that is equal to sigma inside the bracket T raised to 4 minus T0 raised to 4. So this is the application of Stefan's law of traditions, that is loss of heat energy per unit area per unit time of the perpetual black body, that is equal to sigma inside bracket T raised to 4 minus T0 raised to 4. Thanks for watching my lectures.